Hey everybody, Mrs. Bodechon here. Today we're talking about chemical bonding and the different types of bonds. So first thing we're going to look at is going to be the Lewis dot diagram. This is also known as a Lewis structure, and we're just going to kind of figure out how to do this really quickly. So you are going to put dots around the chemical symbol according to how many valence electrons your atom has. So we're going to do neon because neon is a noble gas and it has 8 valence electrons. So this is going to be the maximum amount of dots that you're going to have around your symbol. You're going to first start with your dot on the right hand side, and then you're going to go the top, the left, and the bottom. And then we are going to repeat this pattern right, top, left, and bottom. And as long as you follow that, you will get the Lewis structure right every single time. So I want you guys to pause this video and try to do carbon really quick by yourself. All right, let's go ahead and look at the answer. So carbon is in group 4A, which means it has 4 valence electrons. So we will be putting 4 dots around our C symbol for carbon. So we're going to start right, top, left, and bottom, and that is our Lewis structure for carbon. Okay, let's get into intermolecular and intramolecular forces. Those words look very similar, so make sure that you're really looking at the beginning of the word to see if it's the tra or the ter, okay? So here's a diagram of the difference. Intramolecular forces are the forces that hold the molecule together within the molecule, okay? So we're talking about inside one particular molecule only. And then if we're talking about the intermolecular force, we're talking about how molecules are held to another molecule. So this is the force that holds molecules together from another molecule, all right? All right. Let's look at this. Here we have oxygen and we have iron. And oxygen and iron go together really, really well. They bond easily. Why would oxygen and iron bond easily together? Well, if we look at their valence electrons, oxygen has 1, 2, 3, 4, 5, 6 valence, and iron on the last valence shell only has 2. Well, we know every atom really wants to have a full octet. That means 8 valence electrons in its valence shell to make it stable. So if we add up 6 plus the 2, they will bond together and we will have 8 valence electrons, and each atom will then be stable and happy. So they work together very, very well. There are 2 types of bonds that can happen. The first one is a covalent bond, and the second one is an ionic bond. Yes, there's another one, and we'll talk about that one in a second. But the covalent bond, it looks something like this, and this is where we are sharing electrons. So you can see that there is more of an overlap happening in our energy levels because our electrons are being shared. So there's kind of like a crisscross happening. And then we have ionic bonds. And ionic bonds, there is a give and a take of electrons. Okay, so there's like a donator and an acceptor to the electrons, and you can see that happening here. We call it an electron transfer. So let's talk about ionic bonds first. This is going to happen between metals and non-metals, and you can see that on the periodic table where they're located really fast to determine if it's an ionic bond. And you can see that we are transferring this valence electron has 1, atom B has 7. So in order for it to have a full octet, atom A will transfer that electron over to atom B, and you can see it ends up right here. So then atom B has a full octet, which is wonderful. Well, atom A, this valence shell will dissipate, will kind of just disappear because it no longer has an electron on it, and it will be a full inner shell, and it will be stable as well. Well, what ends up happening, because we donated an electron, or we transferred that electron, atom A is going to become positively charged. It's going to become a cation, as represented right here. And then atom B will become an anion because it accepted that electron or gained that electron, right? So it's an anion. Well, what do we know about positives and negatives? They attract one another because they're opposite. So all of a sudden we have this electrostatic clinging, and it will attract the positives and negatives, and they will stick together. And that's what forms our ionic bond. So you can see here sodium and fluorine. Sodium is donating its 1 valence to fluorine with 7 valence. And you can see they become cation and anion, and then all of a sudden they will do that electrostatic cling and be together ionically. All right, let's move on to a Bohr diagram. You can see we have sodium and chlorine, and I wanted to show you what this looks like in an ionic bond. You can see sodium has 1 valence and chlorine has 7. So we are donating this 1 valence over here to chlorine. So what does it look like? You can see the difference in electrons because they've used X's and dots just so you can like kind of see it a little easier. Notice the outer energy level on sodium has disappeared. So there is no more. But what does that leave us with? That leaves us with a full octet underneath that for sodium. So sodium is stable now and happy because it has a full octet. It also is now a cation. And then we have chlorine, which became an anion, and it is also stable and happy with its full octet because it received one from sodium. And they will cling together because opposites attract. What does this look like in a Lewis dot structure? So we have the 1 valence and the 7 valence, and the arrow is representing the give and the take, right? The transfer of the electron. And then we can see it becomes cation and anion, and then we end up with sodium chloride, them as an ionic compound. So I want you guys to try one. Try to do a Lewis dot structure of magnesium ionically bonding with oxygen. Go ahead and pause your video and try it out. I'll give you the answer in a second. All right, let's go ahead and check it out. So here we go. Magnesium is in group 2A, so it has 2 valence electrons, and then oxygen is in 6A. It has 6 valence electrons, so we have those 6 dots there. And you can see the arrows are representing the spots that they are filling in on the Lewis dot structure in order to become a full octet. So we have magnesium becoming a positive 2 cation and oxygen becoming a negative 2 anion in order to make magnesium oxide. You can look at this in a Bohr diagram and it looks very similar, right? We're going to have these 2 valence and they're going to come over to oxygen. So they're being transferred to oxygen, and then we can see that they all end up with a full octet because magnesium's outer valence shell disappears and it's left with a full outer octet, and then oxygen received 2, so it's a full octet, and they cling together because they're positive and negatively charged. We're going to switch gears and we're going to talk about covalent bonds now. So covalent bonds are going to happen between 2 or more nonmetals bonding together, and this is a share of valence electrons. So we're not giving and taking anymore. Now this is a mutual share, okay? And you can kind of see this happening with our 2 hydrogen atoms, how we have an overlap of those energy levels because they are sharing the electrons. So Lewis dot structure for chlorine and chlorine covalently bonding, you can see that we have 7 valence electrons each. Well, we only need 8. So we're not going to share all 7, right? We're just going to share 1 each. This is called a single bond, by the way. And I circled the overlapping sharing electrons. So 1 from this chlorine and 1 from this chlorine. Therefore, they both have a full octet, and that's all they need to share. If you look at it with a Bohr model, you can see that we have 7 and 7 valence, and then you can see the overlap of where we are sharing 1 electron from each atom is sharing. Therefore, we consider this a single bond. There are different types of covalent bonds. We have polar and nonpolar bonds, and they are a little bit different from each other. So a nonpolar covalent are where we have electrons that are shared equally throughout. And then we have polar covalent where electrons are shared unequally or like asymmetrically. This is where we're going to have a partial charge. So a partial positive and a partial negative happening on sides of our compound. So you can see here, we're talking about nonpolar. So nonpolar, if they're true nonpolar, they're going to be called diatomics. There are 7 diatomics. These do not exist in nature alone. They'll always be together like a pair. And you can see this is the 7 right here. We have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And you can see their chemical formulas. So it's just going to be F2O2 and so on and so forth, because they do happen as a pair. They're always going to be together. And this is just showing you hydrogen and how they come together as a nonpolar diatomic covalent bond. So where are they at and how can you memorize these easily? If you look at the periodic table, there are 7 of them and they make a number 7 on the periodic table, plus hydrogen. Don't leave out hydrogen, right? All the way over here, he's not part of the number 7, but he is one of the 7. So don't leave him out. All right, let's talk about polar covalent. That's going to be where the molecules have one side which is slightly positive and one side which is slightly negative. And you can see these symbols right here. This is going to mean slightly positive. This is slightly positive. This one's going to mean slightly negative. So you can see that we're kind of lopsided. It's asymmetrical, so it's not perfectly symmetrical, right? We're kind of lopsided here. And you can see that there's going to be different electronegativities. In other words, some side is going to be a little bit positive, some side is going to be a little bit negative. And I'm just showing you a couple different ones here, hydrochloric acid and water. And then I showed you what a Lewis structure of water would look like for the polar covalent. So I have a data table here for you of polar covalent electronegativity differences, because electronegativity tells you how charged it is, right? So is it just charged a little bit or is it charged a lot? Are we getting really close to ionic even? Like, where are we at? So if you see that our numbers are going up, we're getting more and more polar, in other words, more and more closer to ionic. And if we go down in electronegativity, we're getting less and less polar. We're getting, in fact, closer to nonpolar, all right? So you can kind of see all of these, for example, start with hydrogen. So you can kind of look at them. They're all starting with hydrogen, and then they have a non-metal after that because, of course, covalent's all non-metals, right? And you can kind of see this diagram here. The difference in colors is the difference in electronegativities. So you can see this one is very lightly shaded. So this is going to be very, very low. In fact, if you look, it's only 0.4. So we're headed really close to getting into nonpolar. And then as we move up with these drastic color changes, you can see our electronegativity increases. And we're getting closer and closer to ionic, but we're not quite there yet, right? So here's just a little chart for you to help you understand where the electronegativity start and stop. This is not perfect. In fact, if you look this up, every chart's going to be slightly different, okay? So if it's a true nonpolar, it will have a 0 electronegativity. However, they do say that there's nonpolar ones out there from 0 to 0.5. Sometimes you're going to see it say 0.4, somewhere around that area. And then as we go up, we'll get into polar next, and that's going to be somewhere around 0.5 to 1.7-ish, right? You can see this one's a little bit different, and they all will be slightly different when you look them up, okay? And then from 1.7 all the way to 3.3, or we can just say 1.7 and greater than that, right, is going to be your ionic bonds. And this is just based on the electronegativity. Something to note is these are going to be weak, and this is going to be strong over here, okay? So which model shows polar covalent compounds? Go ahead and pause your video and try to figure this one out. All right, let's go over the answer. So here are your polar covalent compounds. How can we tell? We can tell because these are going to be your ones that are the most asymmetrical. Okay, we have a partial negative and a partial positive. These are asymmetrical too. Notice this one is perfectly symmetrical, so that's going to be nonpolar. Because this one is symmetrical, it's probably going to be nonpolar. However, it does say partial negative and partial positive. So this one's going to be very, very low electronegativity, not perfect nonpolar. So not diatomic, but this one's probably going to be like 0.2, maybe even 0.3 electronegativity, okay? Really, really close to a perfect 0 though. So these two are going to be your best bets for a polar covalent. All right, which model would be nonpolar covalent compound? Go ahead and pause and we'll go over the answer. All right, let's check it out. Nonpolar is going to be the one that looks asymmetrical, right? So the one that is, that looks symmetrical, not asymmetrical. So the one that looks the same on both sides, in other words. So this one looks perfect on it. Like if I drew a line down the side, it would fold over and be perfect. That's symmetrical, right? And this one would not have a charge either. So we can see positive and negative, and we can see partial positive and partial negative. This one does not have a charge, so that is a clear indication it's nonpolar. In fact, that would be a diatomic. Okay, which model would be ionic? So go ahead and pause your video, and then we'll talk about it. All right, let's go ahead. The red one is definitely going to be the ionic bond. We can tell because we have a full positive and a full negative charge. Another way is they're not touching completely in this model, right? When we draw models of ionic bonds, we don't draw them touching, because when we draw them touching or overlapping, that's representative of sharing electrons and a covalent bond. So ionic, remember, they just have that electrostatic cling. So they're going to get really close to one another, but they're not actually going to overlap those energy levels like a covalent bond does. Okay, so what are we missing? We're missing another bond. Just throwing this out there for you, a little tidbit, okay? Metallic bonds do exist, and that's going to be mostly between metals. And there's going to be a result from the electrostatic attraction between the metals and the cations and the delocalized electrons. And there's this whole sea of electrons that's happening, and you can see this in between the positive charges. And this allows electricity to flow through those electrons in that sea of electrons really easily. But we're not going too far in depth. This is all you need to know, is that metallic bonds do exist. They are out there, but that's pretty much all you need to know. So thank you all for watching. Tune in for next time. Hit that subscribe button and like this video. Thank you so much. Bye, everybody.